In this video, we're going to learn or review a few theorems that are related to the Laplace transform to find some very fast ways to analyze dynamics in circuits. To start this process, I'd like you to pause the video and try to write down the most common shapes for waveforms that are applied to circuits. The two that sprang to my mind are sine inputs, which are easy to analyze using transfer functions or Bode plots. You know, a sinusoidal input will have a sinusoidal output. Or step inputs, which require some more involved math. If you want to calculate the step output of a circuit, you could use an inverse Laplace transform or solve a differential equation, but both of those are kind of tedious math to do like at a lab bench. Or you could pattern match to some known transfer functions where you just happen to know the step response for them. But circuits tend to present lots of minor variations on a theme that make pattern matching kind of tough. So we'd like to come up with a new way to solve the step response of circuits, one that's ideally faster. We have a few advantages in doing that. First, most amplifier circuits, or other circuits that we're going to deal with in this class, can be approximated as first order. And so that simplifies the type of responses that we expect to see. Second, impedance makes it really easy to find transfer functions. So if we can use transfer functions to quickly identify the distinguishing features of a first order circuit, which are the starting value of a first order step response, which are the starting value, the ending value, and the time constant, then we can really easily describe our step responses. We'll start doing that in just a second, but there are a few other circuit inputs that I want to mention first. Ramp inputs kind of look like DC problems because all of the slopes are constant forever. So we tend to ignore the startup behavior where they might have some dynamics to them and then treat them as sort of pseudo-DC. An exponential rises or falls, like 1 minus e to the minus t over tau, are common inputs to a circuit because resistors and capacitors are everywhere, and we tend to just approximate those as ramps. Alright, so focusing back in, we'd like to find the initial value, final value, and time constant of a step response for this first order circuit in order to really quickly write the step response at V out. We know the response will be first order because there's only one energy storage element in the circuit, the capacitor. So there can't be more than one power of s running around in our Laplace transform. We can start finding these initial values, final values, and time constants by finding our transfer function and then putting it into factor form. We find our transfer function using an impedance divider where the parallel combination of R2 and C is divided against R1. Some only modestly tedious algebra will reveal this factor form, which I think is beautiful for a few reasons. One is that the time constant is immediately visible in the factor form because the denominator is always of the form tau s plus 1. Another is that the factored form does a really good job of separating out DC behavior of the circuit, which is what the circuit would do if signals weren't changing, from the dynamic behavior of the circuit. Which is which is a term that captures the step response of a circuit and other time-varying behaviors. So this first term is representative of the DC gain. This term is called the dynamics, and it captures that sort of step behavior. So, for example, if this circuit were driven by a constant voltage, we could ignore the capacitor because capacitors only pass current if there's some dV dt. And that would result in a resistor divider being left behind. This first DC gain term looks like a resistor divider, and so it captures the DC behavior of the circuit. Because of this split and the easy identification of a time constant, I really like the factor form, and I encourage you to write your transfer functions in it for this class. Next, we're going to find our initial and final values using the initial and final value theorems, which I've included here. These theorems relate the limit of a time domain function to the limits of its Fourier transform times s. One mnemonic I use to remember which is which is that I think of s as a frequency, and remember that high frequency, or big S, corresponds to small time, and vice versa. So I know if s is going to infinity, I must be talking about the time going to 0, and therefore I'm talking about the initial value theorem. So, applying that to our example, the function we care about is v out of t, which is where we'll see our step response. We know that the transfer function from our impedance analysis above, so we'll take the limit of s times v out of s, and then we're going to rewrite v out of s as the product of the transfer function and the Laplace transform of our input step. So here's the transfer function, here's our input step. One trick when you're evaluating the initial and final value theorems for step inputs is to remember that the input itself, v0 over s, cancels out with the s that's hanging out in front of the theorem. So this s and this s cancels out, meaning that you can often get a quick initial or final value just by letting s go to infinity or 0 in the transfer function, in this expression. Doing so with our transfer function reveals these values. So if s goes to infinity, then this term on the bottom is infinitely large, the whole thing goes to 0. If s goes to 0, the dynamics term turns into 1, and we're just left with this divider. So our waveform is going to be a first-order rising shape from 0, that starts at an initial value of 0 and ends at a DC value which is a divided version of v0. I've also included a falling edge on this waveform, which hopefully looks pretty reasonable to you, or sort of common sense or instinctual. This falling edge is correct, but it actually sort of flies in the face of the math we've looked at so far. If we were just applying this exact same technique, but with a negative input step, so minus v0 times u of t, we could just replace this with minus v0 and would expect our final value to be a negative number. So that means that we're missing something in the mathematical description I just gave you. And that trick is that falling edges are v0 times 1 minus u of t. So we can take advantage of the fact the circuit is linear and add the response of the circuit to a DC v0 to this negative step, to this minus v0 u of t. Which shifts our response up by this quantity and results in a falling edge that is continuous with our previous value. The big takeaway there is that the initial value produced by your initial value theorem has to be added to the value of your waveform right before a step comes in. The initial and final value theorems are nice, but we can punch them up by realizing that they have circuit interpretations, which let us draw simplifying subcircuits, and these go super fast. I use this all the time when I'm analyzing circuits. We're going to pursue that technique on this slide, and I've brought our transfer function from the last page so that you can compare our results to those implied by the transfer function. When you're applying the initial value theorem, you let s run to infinity. If we did that with our impedances before we found our transfer function, we'd observe that capacitors all have negligibly small impedance compared to resistors because their impedance is 1 over Cs. That means you can draw an initial value circuit, which is also sometimes called an AC circuit, where many of the capacitors are replaced with short circuits, where they short out resistors. Doing so for our example reveals that the output node is shorted to ground by a capacitor at time 0 plus, so we know our initial value will be 0. And now as a quick note, I hedged my language a little bit when I described how you draw the initial value circuit. You can't always replace caps with shorts because caps are shorts compared to resistors, but not compared to each other. So you need to be mindful if there's more than one capacitor in the circuit to keep both of them, since they will be becoming infinitely small impedances at the same rate as S goes to infinity. We can use a similar technique for the final value theorem that lets us draw a final value or DC circuit. In final value circuits, capacitors are replaced by open circuits. This reveals that the final value of V out is given by a voltage divider on V naught. Finally, we need to find our time constant. If a circuit has only one capacitor, then the time constant is going to be given by the capacitance times the Thevenin resistance seen looking out from the capacitor's ports. This makes sense because any charge moves onto or off of the cap through that Thevenin resistance. In this case, we can quickly see that the equivalent resistance seen from the port is R1 parallel R2. This technique works for single inductors in a circuit as well, and it can also sometimes work if there are multiple energy storage elements in a circuit, but those elements need to be isolated from one another somehow so that they don't result in a second-order transfer function. That kind of isolation either tends to be a lucky case, like two caps that can be merged in parallel, or very carefully designed so that an engineer doesn't need to do as much math. So in summary, we can calculate circuit responses to sine inputs with transfer functions. We've seen that before. We can also calculate circuit responses to step inputs in two ways. Either by applying the initial value theorem, final value theorem, and pattern matching to transfer functions that are in factor form, or by drawing initial and final circuits and then calculating the Thevenin resistance seen from a capacitor to find the time constant.